in just one of the previous videos, I just kept saying rolling a die, rolling a die. Well, in reality, we were actually tossing a coin, right? Sorry for that. So you toss a coin, and then we looked at the situation where like we try to count the number of heads or number of tails and so on. Now I want to really roll a die. And you know that when you roll a die, the outcomes are, so let x be the random variable associated with rolling a die, rolling a single die. And the outcomes, as you all know, is either you get a 1 with probability 1/6, you get a 2 with probability 1/6, and so on, all the way up to the highest outcome that you can get is the probable a 6 with a probability 1/6 as well. Now the question is, what is the expected value of that? In average, what are we expected to get? Well, we can just use the formula that we kept using. So 1/6 chance we'll get a 1, plus 1/6 chance we'll get a 2, plus 1/6 chance we'll get a 3, and so on. Okay, let's just finish it, I guess. 1/6 chance we'll get a 4, 1/6 chance a 5, 1/6 chance we'll get a 6. And if you just add them up, so we can actually factor out the 1/6, 1 plus 2 plus 3 plus 4 plus 5 plus 6, and that's just 1/6 times, you add up these numbers, 10, 15, 21, and 21 over 6, that's 3.5. So in average, when you roll a single die, you're expected to get a 3.5 somewhere, because 1, 2, 3 is symmetric to 6, 5, 4, and somewhere in the average of 3 and 4 is the 3.5. In a similar way, we can calculate the variance of that outcome. Let's do it the long way, I guess. So the expected value of x minus mu, we need to square it. Well, obviously this is mu. All right, so this would be 1/6 chance. The outcome will be x, which is 1. 1 minus 3.5, we need to square it. 1/6 chance, we'll get a 2, minus 3.5, square it. 1/6 chance, we'll get a 3, subtract from it 3.5, square it, and so on. All the way up to 1/6 chance, we'll get a 6, subtract from it the average, and then square it. We can again factor out the 1/6. So 1 minus 3.5 is minus 2.5. When you square it, the minus will become positive anyway. The 2.5 squared is 6.25 plus minus 1.5 squared, that's 2.25. 1.5 squared, that's 0.25, and then the same thing, 0.25, 2.25, and 6.25. Long and behold, if you just add up these numbers and divide by 6 apparently, so we have 6.25, so that will give us 12.5. Actually, let's do it in one more step, hold on. And 2.25 plus 2.25 is just 4.50, and the last one is 0.50. So if you were to add these, 4.5 plus 0.5, that's a 5, so 17.5. 17.5 divided by 6. And if you guys have a calculator like I do, 17.5 divided by 6. Oops, let's do it again. 17.5 divided by 6. 2.9167. So 2.9167. All right. Now I want to go ahead and start doing some simulations. So this turned out to be the average, and then this one, I mean the mean or the average value, the expected value, I should say. And this one was the variance. Before I go further, just for the fun of it, what if the question, the random variable x was not looking at the outcome of a single die? What if we were rolling 2 dice at the same time, and the random variable that we were looking for is the sum of the outcomes of those 2 tosses? All right, so let me just go ahead and quickly check that as well, just for the fun of it. I will directly go to the simulation after that. Sum of outcomes if flipping 2 dice. All right, so y as a result can be as low as a 2. I don't know if you guys remember that, but the outcome that both of your dice will come out 1. So that's the only way you can get a sum of 2 if you roll 2 dice at the same time. So therefore, with probability, well, the first die will come a 1 with probability 1/6. The second die will come a 1 as probability 1/6. 1/6 times 1/6 is 1 over 36 chance. Does that make sense? How about a 3? The sum will come up as a 3. So there's really two ways this can happen. Either the first one will come up 1, the second one a 2, or the first one is a 2, the second one is a 1. So therefore the probability of this one is 2 over 36. Does that make sense? And a 4 will be with probability. So outcome will be 4 if the first die is a 1, the second die is a 3, or the first die is a 2, the second die is a 2, or the first die is a 3, the second one is a 1. So 1, 3, 2, 2, or 3, 1. So 3 outcomes out of 36. A 5 with probability 4 out of 36. So I'll just leave the details to you. 5, 36. A 7 with probability 6 over 36. 8 now is going down again, 5 over 36 and so on. And 9 with probability 4 over 36. Okay, a 10 with probability 3 over 36, and 11 with probability 2 over 36, and finally a 12 with probability 1 over 36. So if this has been a little bit complicated for some of you, what you can do is you can even construct a table. I can't resist, but let me quickly construct a table and you will convince yourself better on what we did. So in this table, the the rows represent the outcome of the first die. So this is the first die, versus the columns represent the outcome of the second die. So if the first one is a 1, the second one is a 1, the total will be a 2. First one is a 1, second one is a 2, the total is a 3. First one is a 1, second one is a 3, the total is a 4, and so on. So you can easily add them up, right? So sorry for that. A 2 and a 1, that would be a 3. 2 and a 2, that would be a 4, 5, 6, 7, 8. 3 and a 1, that would be a 4, 5, 6, 7, 8, 9. A 4 and a 1 is a 5, 6, 7, 8, 9, 10. 5 and a 1 is a 6, 7, 8, 9, 10, 11. And a 6 and a 1 is a 7, 8, 9, 10, 11, 12. So now by inspecting this picture, you can easily identify, for instance, what's the probability that a 2 will come out, a total, because we are looking at the sum of the outcomes, right? So this is just 1 out of 36, because this is a 6 by 6 square inside here, 1 out of 36. How about a 3? A 3 has either here or here, so it's 2 out of 36. How about a 4? A 4 will be 1, 2, 3 out of 36. Do you guys see that? So it's basically the same thing that I did it in my head. You can easily construct a table. For instance, the most likely event is the 7. So you guys can look at 1, 2, 3, 4, 5, 6 of them. 6 out of 36. There you go. 8 is going back to lower, right? So 8 is just 5 occasions, and that's why I wrote it as 5 over 36. All right. So having said that, what is the expected value if you were to flip 2 coins? In average, what are you expected to earn, to get? It turns out that the expectation will be the following. So it will be very painful, I can say that. 1 over 36 chance, you'll get a 2. 2 over 36 chance, you'll get a 3. And so on. All the way up to 1 over 36, you'll get a 12. 1 over 36 chance, oops, let's go this way a little bit, you'll get a 12. And indeed, if you work through all these numbers, so basically multiply this number and that, multiply this one and that one and so on, and then eventually add them up, this comes out as a 7. And at that step, you start scratching your head because, wait a second, 7 is just 2 times 3.5. So when you flip 2 dice at the same time, 2 dice, wait a second, each one in average will get 3.5. And because the 2 dice are independent of each other, so 3.5 for the first dice in average, 3.5 for the second dice in average, so the total should give you 7. So therefore, what we could have done instead is the following. E of y is just E of the outcome of the first event plus the outcome of the second random variable. But we know that expectation is a linear operator. I can split it like this. That makes sense. The first one was 3.5. The second one, in average, we're expecting. So therefore, if you roll 2 dice, in average, you're expected to get a 7. And indeed, 7 is the most likely event here. It is this diagonal. It's the most likely occurring event. In a similar way, you can calculate the variance, but the variance is too ugly. I'm not even gonna go into that. Now what I wanna do is to do some random experiments using a feature called simulation. I will randomly generate numbers. I'm not gonna do it for 2 dice. I'm just gonna do it for the 1 die case. All right, so we are rolling a die, a single die. I'm gonna roll a single die 4,000 times. All right, 4,000 times we're going to roll a die, and I want to see the outcomes. I want to see if in average we're going to get a number which is close to 3.5. Isn't it? Aren't we expecting the average to be 3.5? Let's see if that will come out, that will materialize. And along the way, I want to also look at the standard deviation of the whole thing, the distribution of those 4,000 outcomes, random experiments, and see the result. And then I'm going to do a small trick and see the impact of that small trick. Namely, I'm going to construct a sample with 3 dice. So instead of 4,000 simulations of single dice, what I will do is I will roll 3 dice at the same time, 4,000 times. So 4,000 times I will roll 3 dice and I'll get the average. And then I'll compare. I'll check the expected value again and the variance and see if there's any significant difference. If there is, I should be able to use it to my advantage. All right, so let me open my Excel. Okay, I have my Excel open now. So we are going to do some simulations, simulation number here. So simulation 1, 2, 3, and so on. And here is the outcome. So the outcome is a number, a random number between 1 and 6, right? Inclusive 1, 2, 3, 4, 5, or 6. And first, let me just prepare those 4,000 outcomes. So what you can do is you can right click that cell, scroll it down, up. Excel will ask you to fill the series. If it lets me. Okay, my machine is kind of, extremely slow right now. I don't know what it's doing. Okay, let me try it one more time. So right click on that corner, scroll it down, up, and we want to fill, oh, sorry. Wait, instead of fill a series, let's just do series. What am I doing? All right, so step value is 1, stop value is 4,000, and we want a column. That's it. And press OK. Boom. So we have all the way from 1 all the way to 4,000. So we will do 4,000 experiments. Here we go. So how can I randomly roll dice basically in Excel? It's a very neat idea. It's based on this rand function that we used previously. So remember, rand is just a way to construct random number between 0 and 1. How can I use that to generate a number between 1 and 6? Either 1 or 2 or 3 or 4 or 5 or 6. What I can do is I can obviously multiply this number by 6. Let me just go ahead and multiply that number by 6 first of all. Do you guys see that? Press enter. Now I have, each time I press F9, sorry for that. Function F9 in my case. Do you see how, wait a second, but the roll of a die is not like 4.03, it's either 4 or 3 and so on, right? So I think I need to take the floor of that. So we can take, there's a floor function, which is pretty good. It will return the integer less than that number. Let's see if it works. Close the parentheses. Nice. So let's keep refreshing. Let's see if we 1, 2, 5, 2, 3, 0. Wait a second. Why a 0? And why am I never getting a 6? Oh, so because now when I multiply any random number between 0 and 1 by 6, now I get any random number between 0 and 6. That's not what I quite want, because when I take the floor of that, I will get either 0, 1, 2, 3, 4, or 5. Not 1, 2, 3, 4, 5, 6. I get 0, 1, 2, 3, 4, 5. So I want to really add 1 to it in the end. Does that make sense? Let's try it again. Now it should work. All right, so I can get a 6. And then some other numbers, 6, 3, 2, 5, 6, 1, 4. Okay, it's perfect. So Excel is randomly tossing a die. So first step accomplished. So we have 4,000 simulations. So we basically tossed the dice 4,000 times. Now there's a couple of things I want to calculate. First, let's do some counting. Let's see how many outcomes came up as a 1 or 2 or 3 or 5 or 6 or so on. So 1, 2, 3, 4, 5, or 6. There's a very neat function in Excel called Countif. So we want to count the number of outcomes in this range. Press F4 or function F4 depending on the machine you use. And I want to see this outcome. How many times that outcome came out. 666 times, and then double click. Wow. Let's make sure that this sum is equal to what? There you go. There you go. Okay, perfect. So these numbers add up indeed to 400. So we can exactly see in each time the numbers are very close to each other. If you do an experiment 4,000 times, in average, 1/6 of those outcomes should come out as 1, 1/6 should come out as 2, and so on. And by the way, if you calculate it here, average, in average, 4,000 divided by 6. So in average, we're expecting 666.67. So all these numbers are very close to that. Very, very neat. Well, in fact, why don't we just do the actual average? So so this one was a theoretical average. Theoretical average. We know that the math tells us that the average should be such. But really, the numbers that we have in front of us, what is the average of those numbers? So I want to calculate the average of all these simulated numbers. And indeed, that number is 3.48. Wait a second. Isn't this what the theoretical result told us? Well, sorry. Here I was supposed to further divide by... didn't we say that in average, the average outcome should be 3.5, right? So if you roll a random dice, 1/6 chance you'll get a 1, 1/6 chance a 2, 1/6 chance a 3, and so on. So this is very, very close to what we got earlier when we did the theoretical calculation. Remember this number over here, 3.5. All right, so let's just go ahead and now let me simply put a histogram. I'll just select these cells, insert. You can either directly use this histogram feature, which I usually never do. I would prefer to go with this. So right click, format the data series. All right, and make sure the gap is 0. Don't fill anything. So the fill is empty, but the border, make sure there's a solid line border. Perfect. And oh, by the way, the vertical axis, we want to make sure you format it from 0. So format the axis. So the minimum should really be 0. There you go. Okay, now it makes sense. Perfect. So the number values, it's when you look at it, each time I press F9, see what happens. They're very close to 666. Remember, we said that in average, 666 of the values should come out 1, 666 of them should come out 2, and so on. Well, actually, you know what? Let me also add the data labels on top. There you go. So very close to 666 for each one of them. The average came out like this. How close is it? So this is extremely close, very almost equal to, not exactly equal to, but almost equal to 3.5, right? Technically, this was supposed to be math average, should be 3.5, and yeah, so extremely close to that. Now though, I want to do one last thing here, and I propose that we can do even better than this. Even though that 3.5 was nice and cool and everything, there's a large standard deviation here. Let me quickly check the standard deviation of those 4,000 simulations. So standard deviation of, you can either treat it as a population or sample, it won't make such a difference. So you just select from here all the way to the end, press enter. Let's see the standard deviation. Standard deviation comes out as 1.70 of all these numbers of this population. Now that we are done with the first part of this simulation, in the second part, we'll make the following trick. Let me just go ahead and copy paste this column over here, Control C. Maybe over here, Control V. So instead of simulating a single value, first let me just go ahead and simulate 3 different values, x1, x2, and x3. By the way, each time you press enter, it automatically randomizes some new values here, simulates new values. If it's annoying for you, go to data ribbon, and I believe it was maybe, oh yeah, under formulas, you can see calculation options, you can make it manual. All right, so that will stop. Each time I press enter, it will no longer update these values, which is nicer, I think. All right, here we will basically copy paste the same formula that we used early on. So I can go inside that cell and just pretty much Control C and simulate. Control V. All right, and we'll do it. Well, okay, so because it's not calculating right now, all it does is pretty much the same formula. What I want to actually, you know what? I'm going to do it like this. Bring it like this. Perfect. It makes sure it's the same formula. Now I'm going to double click all the way below. Oh, it's not gonna do it. All right, it's not something that I was expecting. Okay, so we'll just wait until it reaches the row 4000, which is not too far, hopefully. Almost there. 3000, 4000. Okay, awesome. Nice. Now everything seems like threes. It's not. Don't worry. As soon as we press calculator, it will fix that problem. In the meantime, I want to now calculate an average here. Average of those three numbers. Now remember what I said. Instead of simulating 4000 different values of x, I'm going to simulate 4000 triplets, x1, x2, x3, and average them out. And so I will have 4000 averages, and then I will do the counting basically. So this will be just the average, or if you want, let's just write it as a formula. So it is just the sum of those three numbers divided by 3. That's an average. And I'll do it all the way to till the end. Hopefully it shouldn't take too long. All right, there we go. Okay, finally the good stuff. Okay, we're ready to run some statistics. Let's first do the counting, just like we did earlier. Count. Now, actually, let's go ahead and also allow for the calculation as well, because we will need it. Make it automatic again. Okay, perfect. As you can see, when you add three numbers and divide by 3, either it will come out as an integer, or it will have decimal places which ends up with 0.33333 and so on, or it will end up with decimal places like this, 0.6666667 and so on. All right, so just as an example, adding them and dividing by 3, when you add them, this is 13, dividing it by 3, that will be 4.33333. So a decimal, which an infinite decimal representation. If this is kind of annoying, you guys can just select the column, and we can format that column basically so that it's just a number and it's just 2 decimal places, which is good. Now what I want to count is the following. We want all the potential averages. The smallest average of the 3 numbers is if we get a 1 1 1, so the smallest one would be a 1. The next one would be well, 1.3333, so which is really 4 over 3. In fact, the 1 is just 3 over 3, right? Because you have actually, let's write it like this, 3 over 3, 4 over 3. This one would be 5 over 3, and so on. 6 over 3, 7 over 3. So the maximum, oops, how did this happen? Let's just go ahead and make this whole thing as a number. There you go, something like that would be sufficient. Make it just a number so that we're in a good shape. Okay, guys, let's just do this one again. So this one was 7 over 3, 8 over 3, 9 over 3, and so on. Okay, how did I mess up that way? 10 over 3. We will do all the way up to 11 over 3, 18 over 3, right? 12 over 3. I hope I won't forget anything. 13 over 3, 14 over 3, 15 over 3, almost there, 16 over 3, oops, 17 over 3, and finally 18 over 3. All right, now let's count each one, how many times they appear in those 4000 averages. Well, the first one, count if the range first, so we are selecting these averages, 4000 averages, press function F4 or just F4 depending on the machine you have, and then what? We want to count how many of these, and because so we will just drag this formula all the way down. If everything is correct, the sum of all these should be 4000 again, right? So I want to make sure, verify that first. There you go. Awesome, so we have 4000 sums. Now a couple of things we can do about these sums. The first thing is the averages. So what is the average of all these numbers? There's at least two different ways I can think of. Either we can just take, so let's write average. Either we can directly take an average of all those 4,000 numbers. That works. There you go. Or alternatively, we could have done a sum product. Again, the same average. Let me show you both ways. So sum product function, and this is the first array, comma the second array. There you go. So that should hopefully, oh, sorry, divided by 14. F2, oops. Function F2, go inside, divide by 4,000. Actually, let's divide by this number. There you go, it's 4,000. There you go, wow. So we have the average. Wait a second, why are they not equal? Because I think there's formatting here and no formatting there. So let's make sure they are both formatted the same way. Let's make both of them into a number. There you go. And maybe give more decimal places. You guys can see this is the same number basically. Yeah, make sure it's the same number. Awesome. So yeah, either way works, like we said. So let me highlight one of them and now compare it with the average that we got earlier. Now what I want to do is put them side by side. Let's put it here, I guess. Single simulation 4,000 simulation of single numbers versus 4,000 simulations of averages of triples, basically triples. Now what happens is when you check the average in both occasions, in the first one we said the average was this number, and in the second one the average turned out to be equal to that number that we are about to, yeah, that number. Press enter. And finally I'm gonna do one more thing next to it. I'm gonna also put the standard deviation as well so that it can give us a better idea. So the standard deviation in the first case was this number, and in the second case it is, well, we didn't calculate it yet, so let's just go ahead and calculate it. So it's just standard deviation. We decided to use the population, I guess, so just the standard deviation of these averages, and that's it. So the number came out like this number. Let's just, it's inside W23, so it's just, you can say W23 if you want. There you go. So when you compare these two, we just realize that the single simulation, this one, look at the average. The true average is supposed to be 3.5. We know that if you roll a die, a fair die, in average, you should get 3.5. And especially because we repeated this experiment so many times, we should be very close to the correct. And here we are kind of close, except compared with this one is way more accurate. Do you guys see that? It's accurate up to 3 decimal places. This one is only accurate up to 2 decimal places. Let me press F9 just to convince you even further. There you go. Well, this one, it's not very clear. Let's do it again. Usually, the second one should be a better approximation than the first one when you use the average of the triples. That's kind of the key idea, that the takeaway of this lesson actually. So and we can also kind of observe that simply by checking the standard deviations. Look at the standard deviation, the variation in the first set versus the variation in the second set. The average is closer to 3.5 and the variation is smaller as well. You know what, I can even have the range, the distance, the gap between the max minus min. That's a very good thing to measure, so let's do it. So the max of these numbers, those 4,000 simulations, what was, oh sorry, well, obviously in each case the max is 6. Yeah, we can't really quite apply it in this one because the event space is so small, so yeah, we can't quite do it. But here I think it's clear. Standard deviation smaller means we are closer and closer to the to the mean. And just as the record, look at this variation of these observations here, the counts. So the number of 1s, 2s, 3s, 4, 5, 6s, if you repeat the experiment 4,000 times. And let's try to plot this distribution as well. Let's see what will come out of it. you guys will be surprised to see, oh my goodness, look at that. Let's just right click it. Let's just do a little bit formatting here, no gap. I think you guys are used to it by now. And we're going to do no filling. However, there will be a solid border. And secondly, we want to make sure, we add the data labels on top. So you guys can see this kind of normal curve shape here, right? So we are closer to the actual. These numbers are wrong. They are numbers supposed to be these numbers. So let's just go ahead and edit that as well. Format the axis. Oh, sorry, not format axis. We need to select the data for that axis. Sorry for that. Right click again, select the data. And the horizontal really should pick up from these numbers all the way there, except the sum is not there, obviously. There we go. Press OK, press OK. Okay, now it should make more sense. So look at that. We know the true average was supposed to be 3.5. And look at this distribution. It is centered around 3.5-ish, right? So compare the two. Here the information is spread out. It's not clear what the average is after all. But this one, the second one, is way clearer. So what is different in the second simulation that we did compared to the first one? Well, in the second simulation, we were a little bit smarter. We realized that the xi's can vary between 1 and 6. But when you do an average, for instance, 1/6 of the time you will get a 1 here. Versus, in order to get a 1 inside this list, the only way you will get a 1, and you might have to search for a very, very long time, right? We need a row with 3 1s in it, which is not very likely to happen. So if you, oh, here you go. This one happening is 1/6, 1/6, 1/6, 1/216. Versus in the previous cases, it was every 1/6 of occurrences that was a 1. Versus here, there's not many 1s and 6s, right? So inside this average list, it's rather the numbers are kind of averaged it out. So you guys can see here that there's only 13 6s and only 21 1s. So the extremes are much smaller now. The whole distribution of numbers are close to the center. And you can see here that's not the case. It's more like a uniform distribution, as we would call it. So I hope that was useful. I kind of wanted to motivate you for the idea of sample distribution of the sample mean. It's a very important concept that ultimately will lead to the central limit theorem, which is a result which is even stronger than the law of large numbers. So I hope to see you guys in our next video.